Okay, I'm going to live stream on PyTorch here, and I've been doing this previously in Python, but since it's been a couple months here, I'm going to shift gears to moving to Rust. And surprise, surprise, Rust is very well supported for PyTorch. So let me just bring people up to speed here that the main repo here for people that want to care about PyTorch would be to follow this person, Laurent Mazzari. Hopefully, I've pronounced his name correctly. And he's got Rust bindings for the C++ API of PyTorch. If I collect or click on this, we can see here Rust bindings for C++ PyTorch. And I've actually kicked the tires on this quite a bit, and it's actually quite good. So a few things to be aware of is that there's instructions here that say like system-wide PyTorch, etc. Honestly, you don't necessarily need to care that much about this unless disk space is a big issue and you're working on lots of different projects that are using this, and then maybe you do care about this. But if you are okay with it downloading PyTorch each time for each project, then all you really care about is if you are using CUDA. In my case, I am. Then I set this environmental variable called torch CUDA version, and that's it. And once I've set that in variable, I've had really zero issues with getting this PyTorch Rust working. So what would be fun to do is go to this repo where I've actually got a lot of examples cooking, and it's called Noogie Rust PyTorch GPU template. And I've actually, if you want to take a look at this, I've actually got some stuff set up here for people to use that it could help them out, in terms of a Rust GPU environment. And I'm going to go ahead and click on this repo, this code space, and this code space actually has GPU enabled. So what's fun about this GPU based code space here is that I've got the ability to really work actively on building things with Rust PyTorch. So I guess the big takeaway is that one of the things to get started with is how to figure out how to make a new project that is able to take away some of the things that I've already done. So I think I have like a load test here somewhere, like load test. Let's see here, GPU util. So if I cd into here, we can take a look at this real quick. So if I cd into PyTorch GPU util, I just do cargo run, right? And I make a new terminal here. I can type in NVIDIA L1. And we can see that this should be hammering. At least it should be. Not sure why that's not hammering the GPU. Let's try one more time here. Maybe this one is not using the GPU. Cargo. Oh, I think I have to say GPU. The README. Yes, yeah, I have to say GPU. Well, which is good. I'm glad I verified that actually, if you don't run GPU, you're not going to see this hit. But when you do hit GPU, we're actually able to see it's getting saturated, which is pretty cool. This is a neat little way to maybe kick the tires. There we go. Now I'm using the GPU, right? So if you don't have some way to know back and forth whether you're hitting the GPU, it can really cause problems. So I think that would be kind of a fun little PyTorch tool to write is just not do anything too crazy, but to copy what I did earlier here, which isn't that complex. I mean, start like baby steps here and build out like a stress test tool. So that's what I'm going to do. So what I'm going to do is first create a new project. So I'm going to go up here, say I'm going to open up the README as well, so I can take notes, and we can say like, day, 5 A1 live coding. We're going to do a stress test tool. Stress test CLI for both CPU and GPU PyTorch. So I'm going to tweak using the clap library, which makes things a little bit more user friendly. And in order to get started, I'll just say step one would be cargo new, and we'll just call this stress. About that. So let's go ahead and put this in here. Call this stress, and then I'm going to copy the make file into this stress directory. I really like having a make file handy when I'm working on things. You can see here that it's just useful when I'm working on a project. Now, the next thing I'm going to need to do is install the packages. So what I'm going to do is I'm going to look at another repo I've got here, and I'm going to copy some code from it because I want to use some stuff that will help me out. So let's see, let's go. Too bad I can't just sort by what I was just doing recently, but I think I can just copy this. So let's look at this cargo file. So I want to copy the Chameleon tool framework. This is a lot of times how I do stuff. There we go. And then I also want to just copy a little bit of boilerplate code as well, like in the main here. And so we can just copy, I think something like this would be good to copy. I just like to seed things so that I don't have to do as much work. So we've got a main, and we'll just throw this seed in here. And then I'm going to call this a stress test for PyTorch CPU and GPU. How about that? And then we can call this one CPU. And then we can make another one. So I don't even think we need to do anything. We can just say GPU. There you go. Right, so we'll have a GPU and a CPU test here. And then I also need to make a file, right? So I'll say touch. Well, first I have to change into stress. I'm going to touch source lib.rs. I'm going to build out my stress test. And so it's important when you're building out your library. I think the seed, right, the prompt engineering is really important. So we'll say a stress test that, hammers the CPU and GPU using PyTorch. So we have some good stuff here to start off with. And we can, again, look at the other example here, which was this one, to get some ideas. So what did they do here? So they said, let's slice. So I could just even use this as maybe like a note inside the comments, right, to give it some ideas. Like use this as a guide to work from. So I'm just going to throw some stuff inside of here so that again, I've seeded things, in a way that potentially will really be able to help me. And so then what we probably want to do is also make sure that I have the right libraries. So here's the util. Let's look at what I did before. So I have to install the torch bindings as well. So we got to install that. And then we also need to import the right lines. So if I go back to lib here, I think we're good. I think we can start writing code. So we'll say this. And then here's where I would basically say, like build a CPU load test function. to see what it gives us. Let's see here. So let's slice device CPU. What does that look like? So let device, let's slice here. That looks good. Okay. I mean, I think a string. Well, see, we don't need to do arguments or anything like that. So I think that does work. And then we're going to build a GPU right here. Now, we also want to make these public so I can use them inside of my command line tool. And notice this one's CUDA. Let's double check here, CUDA. I think this is all I need to do. So what we want to do is next is go back to the main here, and we want to basically invoke. We want to say like build the main function and import. We want to, the thing that a lot of times Copilot will screw up is it doesn't use the namespace. So we want to put this to the side here. We want to say namespace. All right, so let's see what it builds. And there we go. Look, so it did it. So because I told it the right prompt here, we have, yeah, CPU load test, GPU load test. That looks good. I mean, now here's the magic of PyTorch is, can we get it to compile? So let's say make format, that works. Make lint. This is really the $1 million question. Did we get it to work? Well, the fact that it didn't blow up immediately is a little bit of a good sign. Let's go ahead and take a look at this. So one of the reasons why this will take a little bit of time is that if you're creating a new project that uses the torch bindings and you haven't set an environmental variable that tells it where your system-wide installation is, it's going to download a lot of stuff. That's really the issue. So, fortunately, this code space has a lot of room. I think I have 100 and something gigs of RAM of space, but it is going to take a little bit of time initially because of how much stuff is being downloaded. So you just have to give it a little bit of space to get everything cooking. Now, if I took away the quiet, for example, we would see a little bit more, exactly what's actually happening. Now we could do this though. We could do this. We could say htop. We can actually see what's happening behind the beneath the hood. And you can see actually that it's pegging one of the CPUs right here, and it's doing some work. And we also see that the NVIDIA tab up here is also doing some work. Now, I guess if we wanted to be kind of bold, we could put another tab. So we could have two tabs, right? We could have CPU monitoring here, and we could have GPU monitoring, which is kind of a cool concept actually. And if we dive into this a little bit more, you can see that this build script, this is again what's downloading all of the PyTorch stuff, which does take a little bit of time the first time you do it. And look where it's putting it. It's putting it into target, debug, build, torch sys, and it's building out this build script. So, I mean, it's an interesting problem to solve in terms of building things with Rust. Is, how much stuff do you refer to that's on disk, and how much of it do you re-download again. Because if, again, every time I make a new project on this particular environment, if I have to actually download it every single time, the very first time you compile is going to take a little bit of time, right? And that's exactly what we're seeing here, is it's taking some time to compile. And one of the things that we could do, I guess, is we could even open up another terminal here. We could actually get rid of this, and we could say, make a terminal here, and we could even go into that directory, or we could even say du-sh. We could say target. We can see that's a big, right? That's a big target, like 5.6 gigs of data, right? And if we wanted to, we could even do watch. Right? So we could even take a look at this and see like how much is into this directory every 2 seconds, and whether it's getting bigger or not. Now, I don't know how much that slows it down from downloading, but we should be able to see it's getting bigger and bigger and bigger. But yeah, again, this is one of the issues when you're using something like this. And we can go back to the docs for a second and just look at this, and we say, if we see that, oh, well, there we go. So it's done. We don't have to look, and we can see it was 5.7 gigs. So that's probably the full extent of what happened. Now we have a couple of errors here. Let's take a look at this. So the first error is, or the lint message is error, yeah, expected unit struct. So use struct pattern. Oh, okay. So let's take a look. This looks like an easy one, I think. So 25 subcommands expected. Using struct command instead. Now, do they want, is that what they wanted right here? Is this? Correct. Consider making the acronym lowercase. Okay, let's try that. No variant named CPU for commands. What I need to do is look at another example real quick. And let's see here. What do I got here? So I have commands play. I see. So that's, I think it doesn't like, so that looks good. CPU. There is a variant with a similar name. Variant CPU not found. Oh, there you go. Well, this is, I think one of the issues. It wants it to be lower. It wants it to be the certain case. There you go. That was it. Just kind of a naming issue, and then also the syntax right here was incorrect. So that does appear to be correct. So now is the magic moment. How do I run this? So let's put the notes inside of here. We can say cd into stress. And in theory, we should just be able to say cargo run dash and then say CPU. And this should run a CPU test. So let's try it out. Let's do the main. Actually, let's look at htop here, and let's see what happens. So run the CPU. So it's going to compile it. Lint just put the libraries on, but the compiler actually compiles it. There we go. we got it working, which is pretty cool. So you can see here it's just saturating the CPU, which is nice. And now what happens if we do a GPU? We do GPU, what happens? Stress test. Notice that the GPU is kind of interesting because it still is saturating the CPU, but it also will saturate the GPU, right? So it's basically hitting both, which is very fascinating to look at, right? We're hammering, this thing is completely pegged out, but we're also hitting, basically the GPU at this 22% level as well. So kind of a cool little tool here. So let's actually even check this in, and I'll put a note here, and then say to test CPU for PyTorch, do this. You can say to test GPU for PyTorch, do this. Go run GPU, and then we can say like to monitor CPU memory, run htop. And then to monitor GPU, run NVIDIA Assimilate-L1, like that. There you go. So now that I've got that thing cooking, I think the next question would be, can we do anything more? Well, first, let's just check it in. So we'll say get status, get add, get ignore, add everything, get commit, adding stress test for Rust PyTorch. So that's pretty fun. Uh-oh, we need to do a git pull, merge it, then do a git push. Okay, I'll do git push. So the question is, can we extend this even more? Can we do anything else? I mean, this looks pretty good, but let's slice tensor to device. I mean, it would be kind of cool if I could hammer it even more. I mean, could I build like I don't know, like add even, I don't know how you would send more of a payload to this. Could we say like build a GPU load test that uses threads via Rayon? I don't know. I don't know. I don't know if this would work or not. I would have to install Rayon. Rayon. Now, I'm curious how this would work, but let's try it out. So let's look at the docs for Rayon Rust. Now, could I hammer this GPU even more? Parallel iterators if we click on this, it would look something like this. So let's see here. Traits for writing parallel programs. I think something like this would be, I'm just curious if we could hammer it even more. So if I go back to my lib and I import this here, I'm going to get rid of this comment. There we go, clean that up. And if I import this using Rayon iterator, that sends load to the GPU. What we got here? into par for each GPU load test. So I would go back to the main now, and I would add one more, and we'll call this one how about T GPU, and then I also need to good. That looks like it works. And if I go back to here, I can add another one. It says T GPU, and then if I do take format, oh, CD into stress, take format, quite surprised if this just works, but we'll find out. Whoa, that's surprising. So now if I run this, cargo run, dash, and we'll say T GPU, threaded GPU, what does this do? Try to compile it. And does it do more? Does it hammer it even more? Whoa, it did. Yeah, so we sent more traffic to the GPU, which is what I was trying to do. And if we look at H top here, look, there's less, the CPU is less utilized. Well, that's kind of cool, actually. That's actually kind of nice. So we could even maybe add some docs to this, and we could even say like, could we add more like there are there we go. That's exactly, it's funny. That's exactly what I was going to say. So if we, and if I go back to my documentation here, what we could do is to use threaded GPU application, threaded GPU load test, use cargo on GPU. So that was definitely really cool. Is there anything else I can do? Probably good. That's good. That's a really quite a bit of awesome stuff here. Go get status, get add, and commit. Adding stress test, threaded stress test, where GPU in Rust. There we go. Well, I'll be back in a couple of weeks to do more PyTorch.